Last week you did an activity where you looked at M&Ms in a reactor, and Pac-Man was eating the M&Ms. That activity applied a brute force method to solving the problem. You worked with actual M&Ms or some other small object, moving them in and out of the reactor and keeping track of the concentrations and the numbers of M&Ms in the reactor. You could also have reached the same conclusions mathematically, which is what I'm going to do in this video. So after watching this video, you should be able to write a mass balance equation for a flow reactor with a reaction and solve that mass balance equation in a flow reactor at steady state with that reaction. So the M&Ms example represented an ideal reactor. So this is a completely mixed flow reactor, or CMFR. In this reactor, conditions are identical throughout the reactor, and those same conditions are what is in the fluid that's leaving the reactor. So CMFRs are a useful way to model tanks, especially if they're well mixed. You could also model lakes. You can use the same principles for series of tanks or rooms, or even air above cities. So let's look more closely at the M&M example and how we could solve the problems in your worksheet mathematically using the concepts of an ideal CMFR. So in this example, M&Ms are reacting. That is, they were being eaten by Pac-Man. We could also assume that this system was a CMFR, so a completely mixed flow reactor. I'm going to write here N dot for in and out because we're looking at the number of M&Ms leaving and entering the reactor, and I also have a reaction term. So here I'll just write my mass balance equations. We've got accumulation equals in minus out minus, in this case, the reaction. So what we'll also do, and what we did in that example, was we also incorporated flow rates. So our accumulation term is going to equal the concentration coming in times the flow rate coming in minus the concentration leaving and the flow rate leaving, and then in this case minus the reaction rate, which we might also be including the volume of a reactor, and R is our reaction rate. So here with this term, you always have to remember to be really, really careful with your reaction rates and the units on there. So here Cn is the entering concentration, and C is the exiting concentration and the concentration within your reactor, because it's this ideal completely mixed reactor. So in all of these types of examples, you're either, well, most of the times in a class situation, you'll be given the reaction rate. It might also be a reaction rate that you can look up. You can find reaction rates for lots of common reactions. Or, especially if you're in a more professional setting, you might be measuring your reaction rates. And you can do this in a batch system and then apply that reaction rate to these flow-through systems. Always remember that reaction rates do depend on temperature. So we have lots of different types of reaction rates that you can apply to different situations. So we have zero order reactions. These don't depend on concentration. So in the M&M example, it's more like a zero order reaction because we didn't have any dependence on the concentration of M&Ms in the reactor. Here we have our reaction rate R equals K, which is a reaction rate constant. First order and pseudo first order reactions are going to be some of the most common types of reactions that you find in an environmental engineering setting. Here, R, the reaction rate, equals K times C, the concentration of whatever you're talking about, or K prime times C, where K prime is the pseudo first order reaction rate constant. So remember that pseudo first order reactions, you can basically treat like first order reactions, but they might not technically be first order reactions. We also have second order reactions where the reaction rate depends on the square of the concentration, and third order reactions where the reaction rate depends on the cube of the concentration. There are also many other different types of reactions. One common one that you see in environmental engineering is the Minot equation. So this is for biodegradation. And this particular reaction rate depends not only on the concentration of your reactant, but also the concentration of biomass present in your reactor. So very, very common for wastewater treatment. So here you can see it's a much more complicated looking reaction rate, which includes X, which is your biomass concentration, C, which is the concentration of the reactant, and also K, one half, which is the half specific growth rate of the microorganism. So remember, when you see these complicated reaction rates, always be really careful with your units, but also realize that you're going to treat them very similarly to the simpler looking reaction rates. So remember that units of R are going to be basically the same for all different types of situations, but units on K are going to change depending on the order of the reaction. So again, always be really careful with your units when you're setting up these types of equations. So for our M&M example, we can solve, well, first I'll solve for the steady state M&M concentration. So here we have our accumulation term equals in minus out minus reaction. So I've filled in all the terms here. We've got to be really careful with units again. For this particular example, for K, I used number of M&Ms per second. And then our in and out terms are also number of M&Ms per second. I can rearrange or set N accumulation to 0, rearrange, solve for C, and in this instance I get 0.8 M&Ms per liter. You might also be wondering, how long does it take to get close to that steady state concentration? And basically what you would do here is you wouldn't eliminate that accumulation term. So you can add back in the accumulation term. Here I've got V dot times dC dt, which would be number of M&Ms per second. And then basically you could just integrate this and solve for C. So that concludes this example. After watching this video, you should be able to write a mass balance equation for flow reactors with reactions and also solve those equations at steady state.